Okay, so this is a mixing problem. We've got water coming in and you've got water coming out. Now in the water coming in, initially the tank had a volume of 500 litres in it. Okay, a strong brine with concentration 5 grams per litre is pumped into the tank. So 5 grams a litre is going into the tank. And at a rate of R litres per minute. And then mixed instantly. At the same time, the mixture is being pumped out at a rate of R litres per minute. That's what's coming out. Okay, so that the tank always has 500 litres at any given time. So the volume at any given time is 500 litres because it's not actually changing in there. So how many grams of salt was going into the system? So if we've got 5 grams in 1 litre and you have R litres in 1 minute, then that would mean that if you want times this by R and this by R, then you have 5 R grams in R litres in 1 minute. So going in would be 5 R grams per minute. Okay, coming out. So coming out of the system, so I have this. So coming out, so coming in is 5 R grams per minute. So coming out of the system, this is part B we're answering here. So coming out of the system, they said that there was, let's say about out, it's R litres per minute. But the trouble is we've put 5 grams per minute in, so there's going to be a mixture of salt and water coming out. So we're after how much salt is coming out of the system, not how much water is coming out of the system, but how much salt. The same as this was how much salt is going into the system. So coming out of the system, what you have to do is you get the fraction of salt and you times it by the total volume that is coming out of the system. The total volume coming out of the system. So the total volume coming out of the system is R litres per minute, because that's what it says there. And the fraction of salt. So S is the amount of salt. We let S be the amount of salt in the system, because that's what it says there. And the total volume in that system at any given time was 500 litres. So salt would be S out of 500 times R. So it's SR out of 500. And the total remains constant. Okay, so that's how many grams is going in and how many grams is going out. So what we want to do now is we want to show that this differential equation, so ds on dt equals R on 500 with a negative there, S minus 2500. So that is the rate of change of salt in the system. So it's the rate of change of salt in the system at any given time. So we've got salt coming in. So salt coming in would be 5 grams per minute. Oh, sorry, 5 R grams per minute. I think we found. Go back. Yep. 5 R grams per minute. Here. Okay, so that's what we've got going in. And coming out, we have S on 500 times 5 times R litres per minute, which was SR on 500 litres per minute. So the rate of change inside this system, ds on dt, and this is the key, is the inflow minus the outflow of salt. So the inflow of salt minus the outflow of salt. So that's going to be 5Rg minus 5R on 500. And that would be the amount of grams in the system, coming in and out of the system per minute, because we're interested in the amount of salt. Okay, so that would be, if you're looking at that now, that differential equation now, so it's 5R minus SR on 500. So if you take the common factor of R out, and I'm actually going to take a negative out because I can see there's a negative here out the front. So that's going to be minus 5 plus S, because that's an S. I'm going to make sure you see the S and the 5 look very similar. So that's minus R, S on 500 minus 5, and if you get a common denominator, that would be S minus 2500 on 500. And that means you can take the R on 500 out, S minus 2500. And that's how you get that differential equation. Going on to solve that differential equation then, you just have to split it and put the R's together in there. So that the R actually is the R is a constant rate and the S is actually your variable. So you'd go ds 1 on S minus 250 equals minus R on 500 times dt, and that's what you'd be integrating. Okay, so just looking at this one, we have a tank of water, 500 litres again, okay, 200 litres of brim in salt water. So it contains 200 litres in it. So there's already salt in it, with 500 kilograms of salt dissolved. 200 litre bream, the tank contains 200 litres of bream, salt in water, 500 kilograms, 50 kilograms of salt in it. Okay, so pure water is pumped into the tank at 20 litres per minute. So there's no salt going in. So there's no salt going in. At the same time, the perfectly mixed bream in the tank is pumped out at 15 litres per minute. But there's already salt in there. So if I was going to set up this differential equation where M is the amount of salt, then dm on dt is the inflow of salt minus the outflow of salt. So the inflow of salt would be 0 because there's no salt going in. The outflow of salt would be the fraction of salt over the total volume times the rate going out. So the fraction of salt in the system would be M over the total in there at any given time. Okay, so looking at that then, so the key here is working what the total volume is at any time. So to get the total volume at any time, so if you want to get the total volume, the water is changing. So you're going to have, at any given time, you have 200 litres of the brine in there. That's just your salt water. All right. And then the change in water, you have, 20 litres a minute going in, and you have 15 litres per minute going out, because that's what you probably notice up here. So 15 going out, 20 going in. So looking at that, that is a difference of 20 minus 5 positive litres per minute. 20 minus 15, sorry, which is positive 5 litres per minute. If there was more going out than was going in, that would be a negative value. So at any given time, the fraction of salt in going out of the fraction of salt in the tank that is then getting pumped out at this rate will be 200 plus, there's a difference of 5 litres change in there per minute. So you put per T, and that's why it's per time. So what you then have to do, this is what's going out, it is times the outflow, the rate of outflow, and the total rate of outflow is 15 litres per minute. So then that ends up being 15m over 200 plus 5t. Now, if there was more going out than coming in, the sign there would have been negative. So if you divide all this by 5, this would be 3m on 40 plus T. And that's where they get that equation from. Because if you look at this now and you come back to down the bottom here, that's going to be equals 0 salt every minute, and then the amount of salt over the total volume would be 3m over 40 plus T. So it's minus 3m over 40 plus T. Now this, when they say find m as a function of time, that 50 kilograms of salt in the tank initially, that's what you use to find your constant, because time equals 0, the amount of salt in the tank is 50. And then it just becomes like solving a differential equation. So you put that on 3m equals minus 1 on 40 plus t dt, which gives me 1 on 3 ln m equals minus ln 40 plus t plus c, and then ln m equals minus 3 ln 40 plus t, actually plus 3c. I could change that to another constant, so ln m equals ln 40 plus t to the minus 3 plus 3c, and m equals e to the ln 40 plus t to the minus 3 plus 3c, which is e ln 40 plus 3t to the minus 3. I could even put that back down there, it doesn't really matter. Oh, actually it'll help me if I put it there. Times e to the 3c. Now the e to the 3c is just your a. So m equals, now e ln a is just a, times a. So that means that then your m will end up being ln, e to the ln a is a, so it ends up being 40 plus t to the minus 3 times your a. So it's a over 40 plus t to the 3. And then when time equals 0, m equals 50, and 50 equals a over 40 cubed, and a will end up being 35,000. Okay, so in order for it to overflow, there's 200 litres in the tank, and there's a difference of 5 litres per minute going in. So if we look at that, that would be 300 litres to fill. So if you did 5 litres and you did 300 divided by 5 litres, you get 60. So that's going to take 60 minutes. So when time equals 60, we can then calculate 32, 40 plus 60 to the power of 3, which is 3.2 kilograms. Okay, so a tank contains 20 litres of water. Dye, 8 grams is dissolved in it of the dye. More water containing the dye with concentration of 4 grams per litre is going in at 6 litres per minute into the mix, and coming out is 6 litres per minute. To set up the differential equation for the rate of change, so let's just let dv on dt be the rate of change of the volume in the water. So it'll just be the inflow minus the outflow. So looking at this, so the inflow, and we're talking about the dye, is 4 grams in 1 litre, and you got 6 litres in 1 minute. So if you times by 6, that would be 24 grams in 1 minute. So going in would be 24 grams per minute. So 24 grams per minute, that's going in. So coming out, we need to get the fraction of dye times the rate out. So the rate out is 6 litres per minute. Do you notice that there's 6 litres per minute going in and 6 litres per minute going out? Therefore, the volume is actually constant, unlike the last one where the volume was changing. So the fraction of dye would be, so if we let the dye be V for volume, and that's going to be the total volume in there at any time times the 6 litres per minute. So the total, we'll put V, the total in there at any time, because it's not changing, because it's 6 minus 6, which is 0, you end up with, you've got 20 litres times the 6 litres. See, what would normally happen is you have the volume, would be the volume that is in there, plus the difference between what goes in and out, and then times T for time. That's if it's a variable volume in there. So this ends up being 6V on 20 going out, which would be minus 3V on 10. Okay. So dV on dt is the inflow minus the outflow. So the inflow would be 24 minus 3V on 10, which equals 240 minus 3V on 10. And then it just becomes a differential equation that you can solve. The 8 grams, that's what you use initially. The volume of dye in there would be 8, and that's what you use to actually find your constant.